welcome back. This is Fundamentals of Micro and Nanofabrication. I am Sushoban Awasthi from IIT Bangalore, and this is the module on physical vapor deposition. In the previous lecture, we looked at some basics, looked at some jargon, looked at understood molecular flow regime. In this lecture, we should focus on one of the simplest and the first physical vapor deposition techniques, evaporation. So the basic idea of evaporation is about as simple as it gets. You have a vacuum chamber and you have a filament, and that filament heats up the material that you want to deposit, and it heats up to a point where either the material melts or sublimes. So that creates this vapor, and this evaporated metal atoms are just transported by line of sight onto the semiconductor and they condense. This is essentially what happens if you take a boiling water and put a lid on top, and if you pick the lid up after 2 minutes, you will see water sticking to the underside. This is exactly the same process. Okay. Typically, this is done in a high vacuum, around 10⁻⁶ -7 torr is maintained while the evaporation is being done, and that is to prevent chemical reaction, because this evaporated metal atoms can often be very reactive, right. So if you are depositing aluminum, it can very easily react with the oxygen in the atmosphere to deposit aluminum oxide and not aluminum. So in order to prevent that, you just keep the vacuum at a lower value. You can, if needed be, like you can do some version of a reactive evaporation. So if you want to deposit aluminum oxide, you can leak in a little bit of oxygen and do the reaction that way. Often the distance between the semiconductor, between the substrate that you want to do the deposition on and the filament is pretty short, and that is for material efficiency. But if you make it too short, then you get non-uniformity. So some of those details we shall look at in the next few slides. Now, other than purity, there is another need for why we want high vacuum, and that is highlighted in this figure. So supposing you try to do the deposition and you do not have the problem of contamination. So supposing you are okay with either oxygen reacting, or you are depositing a metal that does not react with oxygen. So you are okay with the contamination part. So what you will have is you have a high pressure, but that high pressure means you have all these atoms of nitrogen and oxygen inside the vacuum chamber. Because of this high pressure, the mean free path will be very small. So what will happen is, as the metal atoms evaporate now, so this is metal atom gas, right? So this is a gas. So now this gas will interact with the gas already present in the chamber. It will suffer collision, just like kinetic theory of gases predicts. And the short mean free path will basically mean that a lot of this metal will get scattered in various directions. So you expected the metal to come out and go straight and deposit on the substrate, but a lot of the material will just be wasted going left and right and getting scattered in weird angles. You will waste a lot of it. If you, however, were to reduce the vacuum, reduce the pressure and get vacuum, then you would get very long mean free paths, and long mean free paths essentially mean that these red atoms will not interact with any of the blue atoms, and you would actually get line of sight deposition, which will give you higher material efficiency. So that is another very important reason why you want high vacuum when you are trying to do physical vapor deposition. Contamination as well as, so contamination due to reaction, but also for material efficiency. Just to give you some numbers using the terminology we learnt in the previous lecture. So for evaporation, you are doing a deposition. So one thing that you would like to be cognizant of is the time to a monolayer or impingement rate, right? So supposing you are at 10⁻⁶ pressure, so the monolayer time is around 10 seconds. So in 10 seconds, whatever trace gases are present in the chamber would form a monolayer if the sticking coefficient is 1, right? That is the worst case scenario. During this time, you are also doing your actual deposition. So you are depositing your metal atom. Now supposing you are doing this at a deposition rate of, I don't know, 1 nanometers per second. So in the time it took the impurities to form one monolayer, you deposited 10 nanometers, right? So 1 nanometer, sorry, so 1 nanometer per second, so in 10 seconds 10 nanometers. So you deposited 10 nanometers. So now that 10 nanometer in the worst case has one monolayer of impurities. So that is the amount of impurities inside the film that you have deposited. So if you want a purer film, either you increase the growth rate, so you sort of evaporate faster, or you get a lower pressure which increases your monolayer time. So within the same thickness and the same growth rate, you actually have lower amount of impurities in your film. So this is what is sort of what is behind the concept of this arrival ratio, that for every source atom that you want to deposit, you get an impurity. How many impurity atoms do you get? And for pure films, this should be much more than 1. So if you want 99.99% pure film, then this arrival ratio should be 1 in 10,000, right? So this is the arrival ratio that you would actually get for various base pressures, assuming a certain amount of melt vapor pressure. So when you melt the liquid, or if you melt the metal, it will form a certain vapor. So that vapor pressure is, say, 10 power minus 4, and your base pressure is 10 power minus 3. So there are 10 times more impurities inside your chamber than there are real atoms, so your arrival ratio is 0.1. So for every 1 atom of real thing that you get, aluminum that you get, you actually get 10 atoms of something else. So that is obviously not good. So you cannot do evaporation at low pressure conditions, right, under low vacuum conditions. You need the high vacuum, because only when you get to -6 do you actually have an arrival ratio of around 100 or 1000, which is coming close to the 99.9 type purity that you are seeking. This sort of also highlights why it's very hard to get device quality material through evaporation. No matter how hard you try, you are never going to get 10-9 purity of the deposited material, something that CVD gets easily, right? So that's the limitation of the physical vapor process. The background pressure always introduces impurities that are very hard to reduce, and if you and to get very low vacuums is very hard and expensive. This is what a typical evaporation equipment looks like. I've actually taken this figure from this reference. So you have a vacuum pump, you have an isolation valve, you have some way of creating the vapor. So you have some way of resistively heating it. Often this is done by electric current. So you just resistively heat some material, it melts and comes off. Deposition is often done far away, so you mount multiple wafers. You don't want to do a single wafer because it takes a lot of time to get to base pressure, so you might as well do a lot of wafers in one shot. I would just highlight but not discuss it. So there are sort of two circular regions made here, right? So one is for uniform geometry, which is this circle, and one is for lift-off geometry, which is this circle. I will not discuss it right now. This will be something that will come a couple of slides later, right? Now the other thing we need to understand is that this thermally melted material must be in some crucible, no? So that crucible must be able to withstand the melted material without melting itself. So something to keep in track. And this vacuum pump system must be good enough to get to -6, -7 ranges. So let's now look at some math. So evaporation rate is a function of the pressure as well as the temperature. So now we are talking about the temperature of the material. So the impingement rate, and this is not the impingement rate of the background gas or the impurity gas, the impingement rate that you would actually get when you have the vapor of the material that you are trying to evaporate. So that depends upon the pressure and inversely on the temperature. You can actually calculate from there a mass evaporation rate, which looks something like this. Here PE is the pressure during evaporation. So when you turn on the evaporation, you create this metal vapor, and that vapor pushes the pressure of your chamber up. However, you also have a base pressure, right? So this is the pressure that you have in the chamber when you pumped it down. So there is this amount of impurity. And what matters for this formula is the difference between the evaporation pressure and the base pressure. So for purity, you want the base pressure to be as small as possible. Then the amount of mass loss is given by this formula, which depends upon the area of what you are depositing on, area that you are evaporating from. So larger crucibles will give you more mass loss, which will give you higher deposition rate. The thing to notice, however, again, I don't want you to remember any of these formulas. We shall not quiz you on it. You can always go back to the lectures and look at these formulas. However, the concept that I want you to remember is that the vapor pressure is a very strong dependence on temperature. This vapor pressure, what is this PE? Hidden in this PE is a very strong temperature dependence. The temperature dependence is not weakly polynomial as this formula on first sight suggests. Inside this PE is a very strong function of temperature. So a little change in temperature can actually change the partial pressure significantly. So here is an example of what the vapor pressure of various metals is at different temperatures. And you see they very quickly, within very small change in temperature, you can actually go from -6 vapor pressure to -2 vapor pressure. Now, because we are doing the deposition in high vacuum and you want the arrival ratios to be at least 100, we want the vapor pressure of the material we want to deposit to be at least -4. Okay. But it can be about as high as -2. We do not want any further, because above -2, once again we run into the issue of too little mean free path and not enough material efficiency. So, this is the acceptable range of vapor pressures that we want to have inside our evaporation system. So, for these vapor pressures, different elements would require different temperatures, right. So, sodium would require a very low temperature, indium would require a very low temperature, but platinum would require a much higher temperature. That is why different metals have required different amounts of power to do the evaporation. The other thing to notice here is that tungsten and molybdenum have very, very low vapor pressures, or at least take very, very high require very high temperatures for appreciable vapor pressures. This is why these are called refractory metals. These are metals that can withstand very high temperature. Often these materials are used as crucibles to hold other metals while they are doing evaporation. Now, what that tells you, however, the thing to notice is that everything has a vapor pressure, right. So, supposing you are doing aluminum evaporation and you put aluminum in a tungsten crucible, and you were doing aluminum evaporation at a temperature such that the vapor pressure is -3. So, this is the temperature at which you get the aluminum will show a vapor pressure of -3. At this temperature, what is the vapor pressure of tungsten? So, you see tungsten is here. So, it keeps going down, 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 down. So, if you at 1000 degrees C, the aluminum has a vapor pressure of -3, but tungsten has a vapor pressure that is far below -6, -9, somewhere deep below this slide. So, the amount of tungsten that is coming out at that temperature is very, very small. So, even though the tungsten is holding the aluminum, the amount of tungsten impurity that you expect on your substrate is very, very small, because not enough tungsten is evaporating at such a low temperature, which is why you use the things like tungsten and molybdenum as boards. There are two ways of heating. So, resistive heating is the simplest one, we have discussed it. The problem with that is that these refractive elements often have some trace contaminants. So, while molybdenum or tungsten may not come out from this hot filament at typical temperatures, the impurities within these might come in. So, for example, tungsten has sodium impurities, and if you look at this figure back below, sodium has a very high vapor pressure. So, any amount of sodium impurity in the tungsten will come out during evaporation, and which is a problem. So, that is why people moved away from a resistive filament approach to an electron beam, where you again have a crucible, you again have metal, but instead of heating it resistively, you flow a electron beam in vacuum, and you are able to turn it by using magnetic field. So, you direct an electron beam that falls on top of your crucible, and it locally melts just the top region. So, the whole metal piled is not melted, only the top region gets melted. The rest of the metal remains cool, and it is maintained cool by a water cooled hearth. So, there is a hearth and that is water cooled, so it does not allow the rest of the crucible to really heat. So, the crucible is at much lower temperature than the metal. So, that further assures that any impurity in the crucible would not go out, because the crucible is at an even lower temperature, so it has an even lower vapor pressure. The disadvantage of this technique, however, is electron beams hitting metals tend to cause X-rays, which can cause damage in sensitive devices. These things look, let us call esoteric, but these technologies are something that you have seen, and I hope you notice. So, this is exactly what happens inside a bulb. In fact, when the bulb goes bad and you see some darkening of the glass, that is exactly because the filament is evaporating slowly and getting deposited on the glass. Electron beam is also something you have seen. This is exactly what used to happen in the cathode ray tube displays, where the cathode ray is nothing but a beam of electrons, and using essentially the same technologies as in a display, here you are using the same technology to just focus it on top of metal. Okay. A little bit talk about resistive heating. For resistive heating, you typically have these refractive metals, tungsten, tantalum, molybdenum, etc. They come in these shapes that you can purchase from vendors. Sometimes you also need a crucible to hold the small metal pieces that you want to melt and evaporate. So these crucibles are also made of refractive materials, often alumina, boron nitride, graphite, etc. So here are the various types of crucibles, various shapes, various sizes, etc. You can also make boats out of them. So instead of having a tungsten wire, you can have a whole boat made of tungsten, which already has a dimple, and in that dimple you can keep some material, so you don't need a crucible. So there are various ways in which these things come, and there's a lot of variety out there in trying to do different things. Which do you select? You make the selection depending upon properties. So several vendors will give out suggestions of, oh, if you want to deposit metal, gold, please use this type of crucible and this type of filament or this type of boat. You typically don't want alloying to occur. So for example, aluminum and tungsten form an alloy. So aluminum and tungsten are not the best, tungsten is not the best boat to be used for aluminum evaporation. However, gold and silver do not alloy with tungsten, so tungsten is an excellent boat material for evaporating gold and silver. So those kind of details I'm not going to discuss here. I'm just going to leave it at there, that you should be careful when selecting crucible materials, resistive materials, and boat materials. This is what a typical thermal evaporator looks like. There's a steel or a glass chamber that contains the vacuum. Inside there are just two huge hunks of copper that are the electrical contacts. You put the boat in the middle, put some material, flow the current, it heats up. And there is typically also some quartz monitor. This is what measures the thickness, so you have repeatability, and typically some way of rotating the substrate to maintain uniformity. E-beam evaporators, which use the electron beam, tend to be a little more complicated. They still have the vacuum chamber, but then they have the water cooled hearth. So the water cooling inside a vacuum chamber requires it to be a little more complex. It's often made of copper so that it's thermally conductive. And then there are some often mechanical shutters, so you can turn the you can stop the evaporation at will, right? One point of sticking coefficient, like I've used this term before in this lecture, but I have not explained what it means. So sticking coefficient, very simply speaking, is that supposing you have a flux of material coming in, how much of that material stays on the surface and does not get backscattered, okay? So amount that has stuck divided by the amount that has incident is the sticking coefficient. A sticking coefficient of 1 basically means everything that is coming is sticking. A coefficient of 0 means nothing that is coming is sticking, all right? Now, due to the substrate temperature and evaporation being very low, so you're melting the crucible, so crucible is hot, but the substrate is sitting at room temperature, that is cold. So because of the very large difference in temperature gradient, once the material deposits on top of the substrate, there the vapor pressure is, the equilibrium vapor pressure is 0, so anything that goes on top of it cannot come out. It's a one-way street. So the stiction coefficient during evaporation is often 1. A little bit some math on uniformity. So supposing you had a crucible, and for practical purposes assume that the crucible is a point source, and you have a sample, and the sample is mounted a distance r away at an angle phi and a theta, okay. Now the mass arriving flux at the sample is given by depends upon the two angles theta and phi. It depends upon the radius r. I leave you to figure out the math, but if you look at the math closely, you can actually see that for a special case where of spherical placement, this is called spherical placement, where the sample is placed a distance r naught away from from an imaginary center, which is also r naught away from the crucible. So supposing this sample was mounted in a way that it was on an imaginary circle here, these two angles phi and theta are actually equal, so both of these are theta. So in this special case, if you solve this equation, it actually simplifies to this. And this equation is completely independent of theta, it only depends on r naught, which is the same for every sample placed on this imaginary sphere. Point is, any sample placed on this imaginary sphere will actually get exactly the same Zs independent of theta. So if you want to maintain uniformity across your substrates and you have multiple wafers, all you have to do is place those multiple wafers on this imaginary spherical placement area. So that is why when we look at the equipment figure, and I showed you that there is this imaginary circle drawn, right? So yeah, you see this? Where they are mounting the substrates is actually spherical in shape. Why is it spherical in shape? precisely to make sure that the deposition is uniform on all the wafers. So that is why that circle is important. All right. But then there is more to that, right? We are not, previous figure we were talking about wafer to wafer non-uniformity. But within the wafer itself, the wafer is not a curved piece, wafer is a flat piece. So if the wafer is a flat piece, the angle of the impingement of the incoming flux that is at the center is very different from the angle at the edge, right? So there would be some theta dependence across the flat region of the wafer. And you can simply model it, it's very easy to model. These are the formulas. Again, I don't want to remember any of these formulas. The important part is the concept. So the normalized deposition rate would show something like this. So it would be highest in the middle, and as you go towards the edges, it would fall. So what do you do to solve this problem? Well, you keep, if you make the h very large, make the h very large, then for the same L, your L by h becomes very small. So by keeping the substrate farther and farther away from the source, you sort of make it more and more uniform across the wafer. What do you lose? As you go larger and larger R, your impingement rate keeps falling more and more. So you lose material efficiency, you lose deposition rate, but you gain in uniformity. This is the classic optimization that any deposition has to do. Given a certain substrate size, you need a certain distance to get uniformity, but that allows you, that limits your deposition rate and material efficiency. Let's talk a little bit about step coverage. So we discussed that CVD is often very good step coverage because it's temperature radiated, etc. But here there is no effect of temperature so much. Often the substrate is at room temperature. What you have to be careful about is the direction of the incoming flux. So now, if the incoming flux is coming at all arbitrary angles, what you might get in a is like sunlight in New York. So because of the very tall buildings, when the sun shines on New York, the buildings get a lot of the sun, but down on the street level, not much reaches. So same thing will happen here. The material flux is coming on the top, but most of that gets stuck on the top. Very little reaches at the bottom. So the deposition at the bottom and the deposition at the top are very different. That's number one. You can solve this problem a little bit by making sure that the arrival flux is very vertical. So if it is very vertical, you have better chance of getting a deposition here. But even when it is vertical, very small changes in the angle of this, in this angle would essentially again mean that you would not get deposition in the bottom. So unless the deposition is absolutely normal, you will not get anything on the bottom. Even when you do get something on the bottom, which is point number 2, you get very little deposition on the sides, because again the flux is such, and if you were to tilt it, you would get some deposition on the left hand side, but you would get no deposition on the right hand side. Or if you tilt it the other way, you would get a lot of deposition on the right hand side, but no deposition on the left hand side. It's very hard in evaporation to actually get a conformal deposition. ALD gives it to you for free, evaporation does not. So further taking forward the step coverage argument, so you have a deposited film. In general, if you have a uniform flux, which is what a lot of these things are designed for, you would not get step coverage, you would actually get non-conformal deposition. This is very good if you are trying to do lift-off. What is lift-off? We'll talk about it during etching. However, if you are looking for conformal deposition, evaporation is not the best way. You can make things a little bit better by mounting the substrate at an angle and rotating it. This is called planetary motion. So that planetary motion basically means that this arrival flux, the angle of the arrival flux keeps changing, which gives you some amount of deposition, but still not perfectly conformal. If you start heating the substrate, then you can get some amount of surface diffusion, and that surface diffusion enhances step coverage, which gives you a better conformality, but for that you have to heat the substrate, right? All right, so with that, one last slide on nucleation and growth. So we'll not go into details of nucleation and growth in evaporation, but there is a model which is called the structure zone model. The basics of the model are fairly simple to understand. This was the original paper. What they argued is that depending upon what temperature the substrate has compared to the melting point of the material that you are trying to deposit. So supposing you are depositing aluminum, whether the substrate is at, if it's at melting point of aluminum, then there is then the incoming aluminum will see a lot of surface diffusion. That lot of surface diffusion will allow the aluminum to reorganize itself find the lattice positions and grow epitaxially. However, as you back off from the melting point and you go to lower and lower temperatures, there is less and less energy that the substrate can provide the incoming aluminum to orient itself and become epitaxial. So, the films that you would get will get progressively worse in crystallinity until you get to a essentially polycrystalline film. So, that is what is shown here. Okay. Now, this nomenclature of zone 1, zone T and zone 1, zone T and zone 2 is a relatively modern one. The original paper used slightly different labels, but the concepts are the same. Why are they called 1, T and 2 will be more clear when we discuss sputtering. All right. So, in zone 1 you just have random agglomeration, a polycrystalline film, and this happens if you are depositing at less than 30% of the melting point, which is essentially everything, most metals when you are doing the deposition at room temperature. That is why evaporation gives you polycrystalline films. As you go above 0.3 but less than say 0.45 of the melting point, you start getting some texture, you start getting grains, oriented grains, some columnar growth. Only above 0.45 of the melting point do you actually start seeing large grains, oriented films, near epitaxial films. Okay. So, if for some reason you have to use evaporation and you want orientation and crystallinity, you must heat up your substrate. Arbitrarily at lower substrate, typically at room temperature, you would always get a polycrystalline random oriented film. This is just to show the cross section. Why is it called zone T? Why did they just not say zone 1, 2 and 3? That is because zone T is slightly interesting. What happens in zone T is that you do get a columnar structure, but there is a difference versus depth. So, when you start at small values of thickness, you actually have all the different orientations. However, some orientations grow larger at the expense of other orientations simply by again the New York effect. So, supposing the growth rate of one orientation is 20% larger than the growth rate of another orientation. So, even though they both started at the same point, the one that had a higher growth rate would become a little taller. Because it became a little taller, it would actually get more flux. Just like the taller building in New York will actually see more sun. As it gets more flux, it will grow even taller. So, the things that are growing faster tend to grow even faster because they get more flux. So, that sort of competitive growth ultimately leads to the fastest growth rate wins out, right. So, that is actually called that the kinetics decides which growth rate will win. This is not thermodynamically decided, it is kinetically decided. The fastest growth rate wins. So, for very thick layers you actually get the fastest growth orientation wins out, so you do get some texture. But if you look at a cross section, you will actually see that difference. Initially you will see all different types of orientations. As you go further up and up, some of these orientations, you see the small triangle, some of these orientations lost out and got extinct, and the orientation that was growing the fastest kept growing. Okay. So, there is a structure zone model. We will not talk more about nucleation in this lecture. So, with that, let us end on the salient features of evaporation. So, what are its advantages? Advantages is the simplicity. It was one of the oldest techniques in doing deposition of physical vapor deposition. The films tend to be very pure, not compared to CVD, but say 99.99 type % pure. It has limited step coverage, which can be advantage or disadvantages. The arrival energy of atoms is very low. It is a very gentle process. Okay. You would think that, oh, you are heating up, you are melting up, so the atoms that are raising would cause some damage. No, if you actually measure it, it is very gentle. It is a very gentle deposition. So, it can be done on very soft films. What are the disadvantages? You can't do it on refractive elements. You can't do it for dielectrics that are high temperature. You can't do alloys. Why can't do alloys? Supposing you had nichrome alloy. Nickel and chromium had different vapor pressures. When you heat it up, either nickel will selectively evaporate more or chromium will evaporate more. The ratio of nickel and chrome that actually gets deposited will not be decided by their alloy composition, but by the ratio of their vapor pressure. So, it is very hard to do alloy evaporation. You can't do compounds. Silicon dioxide, hard to do unless you do reactive evaporation, which is a little more tricky. If you are using E-beam, you might cause X-ray damage. If you are using filament, you might have some sodium or potassium contamination. Right. So, with that, we come to an end on evaporation. In the next lecture, we shall look at sputtering, which is the more modern form of physical vapor deposition and becoming a little more common.